Hello. Let's talk about Lewis structures. So why is it important? Take, for example, a drug like sulfadiazine. When I look at the label for this drug, I just see a crazy structure. Let's see what we can figure out from it. This is a skeletal structure of sulfadiazine. A surprising amount of information is hidden within its structure. First, there's some stuff that isn't shown explicitly. Every join or bend represents a carbon atom. Let's add those in. Every carbon atom must have 4 bonds. So whenever you do not see 4 bonds, you should add in bonded hydrogen atoms to take each carbon up to 4. Note, the carbons here in red already have 4 bonds, so we don't need to add any more. Now that we know where the atoms are, we can write its molecular formula. In this case, there are 10 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens, and 1 sulfur atom. Thus, the molecular formula is C10H10N4SO2. The bond orders in a molecule can also be important. They influence bond length and bond strength. To determine bond order, we first need to identify alternative resonance structures. Now, in drawing the single and double bonds in the 6-membered rings, we arbitrarily choose this pattern of alternating single and double bonds. But you can have the alternative single-double structure for the left-hand ring, or you can have the alternative single-double structure for the right-hand ring. You can also have it changed in both. Each carbon-carbon bond in the ring appears as a single bond in half the resonance structures and a double bond in the other half. The bond order is therefore an average of 1 and 2, or 1.5. A more convenient way to draw the structure is one in which all the bonds inside the rings have a single solid line and a single dotted line. This indicates 1.5 bonds for a bond order of 1.5. Or, a lot of times, you'll see this drawn with circles. Although this molecule is drawn as if it was planar, it may not be, and the structure has information we need to use VSEPR theory to decide. We first need to add lone pairs to atoms so we can count electron domains. Take, for instance, the sulfur atom. The sulfur has 4 electron domains, so it has a tetrahedral electron geometry. As all of these are bonding groups, its shape will be tetrahedral, with an ideal bond angle of 109.5 degrees. The nitrogen atom on the left is also non-planar. It has 4 electron domains, so its tetrahedral electron geometry. However, as one of these is a lone pair, the shape of the nitrogen will be trigonal pyramidal. The angle would ideally be 109.5 degrees, but as the lone pair is more repulsive, it will actually be smaller, about 107 degrees. A similar situation arises for this other nitrogen, which has 3 bonds and 1 lone pair, and so it is trigonal pyramidal. Wow! So that one diagram gives me so much information. Now you know.